Hi, I'm Kris Rowe with the Performance Engineering Group. So I'm going to give a very brief introduction to OCCA today. You might hear me use the Canadian pronunciation sometimes of OCCA, so I apologize for that in advance. So I'll get to it. So what is OCCA? Yet another portability framework. This one in particular started from Tim Warburton's group at Virginia Tech around like 2013, I think. And so, there's sort of like three main components. There's like the host API, which has C and C++ and Fortran language bindings. And this provides, unified models for sort of all the standard like GPU type concepts like device and memory and whatnot. At runtime, you can select the particular backend that you want to use. And it also provides services for runtime compilation of your kernels and also caching these for future use. The sort of second aspect is the OCCA kernel language, which is like a directive-based extension to C. And this, which I'll get to a little bit later, is translated into backend specific code. So for example, if you're running with the CUDA backend, then your OKL kernels will just get translated into native CUDA code and compiled with the usual like NVIDIA toolchain. And then the last part is there's like command line tools that provide information about the system and can do things like show you what environment variables are set and also show you what the translation will do ahead of time. So each of these things can be used altogether or independently. Most projects that I've come across are using all of them end to end, but in theory, you could just use, for example, the host API and then roll your own native backend kernels. So the current backends that are implemented are listed here. I would say, the preferred backend for Aurora is the SYCL backend. I have used the OpenCL backend even somewhat recently, but I think it sort of has less support and attention. So, use that at your own risk, if you will. All right. So here I've example of a fairly simple OCCA program that allocates some memory and then creates a DXP kernel and calls it. So I'll try to use some fancy technology today. So the first part here we see we're setting up our OCCA device, which calls this function on the left, which we don't necessarily have to worry about the particular details, but whatever heuristics you would use in your application to choose which device, for example, on Aurora, there's like 6 or 12, depending on how you want to think about it. For a particular MPI rank, it's fairly straightforward to create a function that just returns that device for you. And then the sort of second important part here is these lines here, where we're allocating some memory on the device. You can see it's really familiar to a lot of other GPU programming models in that we have like a templated type that we can pass in. This also does the initialization. So, in the second argument, we're passing in the pointers for the host data, and the copy will happen automatically under the hood and is also asynchronous in this case. This middle part's a bit strange, but we'll get back to it later. But you can provide your kernels to OCCA in a few different ways. In this particular example, it's the kernel would be in a separate file, and then whenever we instantiate the kernel class, it triggers JITing under the hood. And then also the kernels are cached. And then ultimately, whenever we want to call our kernel, it's just like calling any other function. And then I think, I guess there's different feelings, I'm sure, about things like garbage collection. But, one of the features of OCCA is that it will free up the memory for you at the end. So you don't have to worry about that leaking. So we'll dive into some of these concepts a little bit more. So just to sort of give some service to like the transparency aspect, OCCA's fairly lightweight wrappers around the various like backend programming models. And so the concepts of device and memory and so on are sort of lifted from CUDA, but the equivalent concepts also exist in SYCL and OpenCL, for example. So in particular, like I mentioned before, on Aurora, we want to be running with the SYCL backend. So a few sort of key points. If you are a bit familiar with SYCL, then you might know that queues can typically be out of order. So one of the assumptions that's sort of fundamental in OCCA is that all of the streams will be in order. And then the concept of a kernel in SYCL is a little bit more opaque than in some of the other programming models. So here I sort of just listed it in a nebulous way, but your kernels will get mapped to like an ND range of parallel for lambda. All right, so there's a few different ways that you can provide kernels. So sort of like old school CUDA, you can have your kernel source in a separate file that gets read in at runtime, but you can also provide the kernels as strings within your host code. This is kind of nice because if you want to do some kind of fancy, kernel fusion to avoid some extra trips through the device memory hierarchy, then that might be something that is useful. And the kernel source languages that are supported are OCCL, but also you can provide your code as like a backend specific language. So in theory, one usage model for OCCA would be to have a code that just uses the runtime only, and then you could have kernels in, say, like CUDA, HIP, and SYCL to like run on the major like GPU vendors. And then OCCA will still JIT and cache those the same way. It will just avoid an extra step of translating the OCCL to some backend specific code. So the JITting mechanism works like a lot of the other programming models. So whenever your host code is executing, the first time that you try to instantiate a kernel, OCCA will look to see if it exists in the cache directory or not. The sort of, does the binary exist is a very nebulous statement. There's checks to make sure that things like the flags that are used for the JIT compilation and any kinds of like defined constants and whatnot are the same. And then if it doesn't exist, it will go through the process of translating your OCCL kernel and then compiling it. Or if you're using a native language kernel, then it will just do the compilation. But if the binary already exists, then it will load that from the cache directory and then carry on its way. We don't make any assumptions about thread safety in OCCA in the sense that, don't assume that anything is thread safe. And we don't have any kind of awareness about MPI. So if you're going to use OCCA in your, HPC code, you'll have to do some work to handle the caching to make sure that, you don't have like thousands of ranks all trying to thrash the disk at the same time. So if that ends up being a situation that you're in, feel free to reach out. We've looked at this problem quite a bit with the NACRS code. All right, so sorry, we're kind of flying through this a bit, but so what is this OCCA kernel language? So it sort of looks a little bit like maybe something like Julia or Python or something like that. But similar to OpenMP, we're just going to decorate our kernel functions and our for loops. So in particular, the sort of most common attributes that you'll see used are this kernel attribute here, and then these like inner and outer loops. So you can just think about the outer loops as being like equivalent to something like a CUDA thread block, and the inner loops as being equivalent to like a particular thread ID. For the most part, the OCCL language is fairly restrictive in that you're going to need to have sort of like tightly coupled rectangular loop nests. So if you want to do some like really fancy like C++ data structures or something like this in your like GPU kernels, probably not the portability framework for you. If you have some kind of like old school like C type computational code or Fortran or something like that, then it's fairly straightforward to translate. In particular, if you have like some legacy Fortran code, Andrew Kirby from University of Wyoming has some nice talks about what their group has done to translate their legacy Fortran code into OCCA. And then each of these attributes is like fairly transparently mapped to the different backends. So we'll sort of maybe ignore this guy for now. It's a bit of a technical detail, but the outer loop index will become either like a thread block ID or your workgroup ID. The inner loop index will become your thread ID. And then there's also the ability to allocate like shared local memory, which is kind of like a user controlled cache, as well as different kinds of like synchronization. So if you were to say, for example, take the kernel here and then either like run it through the command line translation or run a code that calls this kernel and then look in the cache directory, then you'd be able to see both the original kernel source as well as the translated backend specific source. All right, so the command line tool comes baked in with the OCCA library, and it gets installed in the binary directory. It can do some different useful things. So in particular, if you're building OCCA from scratch, it's a good way to check that everything went okay and that you're seeing the hardware that you expect to on your system. It's also a good way to look at the native backend code that gets translated from your OKL kernels to make sure that things are being mapped to that particular approach the way that you think that it should. And lastly, it's a good way to check which environment variables are set so that you don't get some kind of unexpected or strange behavior. Since I know there's a lot of people using NEC at the conference, I'll take a little detour and say a few tips for successfully using OCCA in the NEC or S code, which typically applies to like your user files. I worked quite a bit with Stefan Kirkemeyer to create some convenient wrapper functions around OCCA that sort of help to shield people from typical kind of gotchas. So definitely use these when possible. And also, use the pool allocated memory whenever possible, since this will help to avoid some extra overhead. If you're not sure about that, check the example cases that come with the netcode. And then the second one is make sure that you're using the SYCL AOT flags for the kernel jitting. Since we're already handling the caching in OCCA itself, we don't want to sort of go through the extra overhead of, compiling to like an intermediate representation in the SYCL runtime. All right, so I'm sure that was entirely way too fast for most people, but if you need any help, then I think a good place to start is always GitHub discussions, because, sorry, if you have a question, it's statistically likely that somebody else might have the same question. If you have some kind of complex topic, or you're interested in getting into some kind of hands-on development and getting stuck, there's an OCCA Slack space that you can join. And if you have some questions about something specific to Aurora or any of the other ALCF systems, feel free to reach out to me directly, and I'll try to help you as best as I can. So that's all that I have for today.